For this section, we'll be introducing functions with their notation and how to evaluate them. So we'll start off with the definition that says a relation is a set of ordered pairs in the form x, y. In other words, a relation is basically a bunch of coordinates that you would normally graph. From here, our next definition says that the domain represents the x values of the relation or the inputs. So the domain represents all the values that you put into the relation. And our next definition says the range represents the y values or the output. So the domain is what you put in. What you say, I want to know what happens when I plug in the value x equals 2. And the range represents what happens when you plug in x equals 2. You get something like y equals 4. So the domain is all of your x values, the range is all of your y values. With that, we say that a function, which we'll call f, is a relation such that no domain value goes to more than one range value. In other words, in order for something to be a function, no x values are repeated. You cannot repeat a single one. If you do, it fails being a function, and it's just a standard equation at that point. So, let's go ahead and look at these two sets of ordered pairs, meaning sets of points. Whenever you see a curly bracket like this on each side, it means you're dealing with a set, which comes up a lot in higher levels of mathematics. So we'll say for this example, we want to decide if the set of ordered pairs is a function. We have the set that contains the point 1, 2, 3, 2, and 4, 7. Take a moment, think about what our definition for a function says and if this is a function. So in this case, yes, this is a function. It is perfectly okay to repeat y values, but you cannot repeat x values. So we go through this and notice we used x equals 1, x equals 3, and x equals 4. So no x values were repeated. This is a function. Now for the next one, go ahead and pause the video, see if you can't figure out whether this is a function. Okay, so we have the points 0, 5, 1, 4, and 0, 2. Notice we repeated x equals 0 because we repeated an x value with different y values. So it's okay to repeat the same point, but because these are different points, this means no, this is not a function. So continuing from here, we have a notation that says y is equal to f of x. So when we talk about function notation, we use the notation f parenthesis x parenthesis. And this tells us that y is a function of x. Why is this useful? Why are we even going through this? Well, if you think about it, if I wanted to evaluate some y value given an x value, I would have to say y equals 2x plus 3, for example. Find y when x equals 2. But instead, we can just use find f of 2. If this were written in the function notation, f of x equals 2x plus 3. So it makes the problems a lot more condensed. As you go through mathematics, you'll find that it's all about shortening the amount of work you need to show, and this is just one of those cases where function notation dramatically shortens the amount of work you'll have to show. Okay, So for our next example, we're going to let f of x equal 2x squared minus x plus 4, and we want to find f of 2. So to find f of 2, remember that means find y when x equals 2 is really what find f of 2 is saying. So f of 2 means we're going to take 2 and plug it in for every x value. Find y when x equals 2, so just plug 2 in for every x. So that gives us 2 times x squared is 2 squared, minus x means minus 2. Oh, I didn't mean to put a negative there, I apologize. Minus 2 plus 4. So simplifying this, we get 2 times 2 squared gives us 2 times 4. We have to take care of the exponent first for order of operations. Minus 2 plus 4. 2 times 4 gives us 8. Minus 2 plus 4. And now finishing up our order of operations, always remember when you're left with just addition and subtraction, you go left to right. So 8 minus 2 gives us 6 plus 4. 6 plus 4 leaves us with 10. So for our answer, we'll say f of 2 equals 10. The function notation must be written in your answer because this is you completing the sentence, essentially, to what the problem used to say. So rather than saying y is equal to 10 when x equals 2, instead you're just saying f of 2 equals 10. The same thing, but a much faster way of approaching it. For the next one, we have f of x equals 5x minus 3. We want to find f of x plus h, and then we want to find f of x plus h minus f of x all over h. To find f of x plus h, it's going to work the same way as when we found f of 2. We're plugging in x plus h everywhere we see an x in the original problem. So that's going to give us 5 times x is now 5 times the quantity of x plus h minus 3. Always remember, whatever is in parentheses next to this f replaces wherever you see an x in the problem. So distributing this 5, we get 5x plus 5h minus 3 is equal to f of x plus h, and that gives us the first part of our answer. Okay, so from here, now we need to find f of x plus h minus f of x all over h. This is a little tricky, but go ahead and see if you can try to figure this out from what we've already done in this problem. Take a moment to pause the video. Okay, so trying this together, notice we need f of x plus h, but we've already found it. That's one very nice thing about function notation. Once you evaluate it, you don't need to do it again. So we can just take what we found for f of x plus h and plug it in immediately. So f of x plus h is just 5x plus 5h minus 3, and we're subtracting f of x, which we already know is 5x minus 3, but remember we're subtracting the entire f of x, so we have to put parentheses around this entire term, these entire terms that is, and this is all divided by h. So we have to start simplifying. We're going to get rid of these parentheses by distributing that negative. There's nothing in front of these parentheses, so they'll just go away, giving us 5x plus, sorry, not minus, plus 5h minus 3 minus 5x plus 3 all over h. And now notice we have a 5x minus 5x. Those will cancel out. We have a negative 3 plus 3. Those will cancel out, which will leave us with just 5h in the numerator divided by h in the denominator. And now h divided by h cancels out, leaving us with just 5. So f of x plus h minus f of x all over h is equal to 5. And this is a very important formula that'll actually come up quite often as you go through mathematics. This is the formula we use to find a derivative. So as you get into the initial parts of calculus, you'll see this come up quite often. Okay, so moving on from here, the last bit that we have for this section is talking about getting things in terms of function notation and then deciding whether or not a graph represents a function. So for this first example here, we need to express w as a function of g. So that means we are getting w equal to something involving g. Just like we say express y as a function of x, y equals f of x. Well, in this case, express w as a function of g means we are trying to find w equals f of g. So how do we do that? Well, we have to get w completely alone, just in terms of g on the other side of the equation. G and constants, that is. So the first thing we would have to do here is subtract this 6g from each side. Since we have 6g plus 2w equals 12, we'll subtract 6g from each side, which gives us 2w equals 12 minus 6g. We'll write it in order variable first. So negative 6g plus 12. And then we can divide each side by 2, which gives us w equals negative 6g plus 12 divided by 2. You could factor a 2 out of the numerator or just divide each term by 2. And when you do that, you get negative 3g. Negative 6g divided by 2 is negative 3g, plus 12 divided by 2 is 6. So w equals negative 3g plus 6. This is w in terms of only g and constants. So we have found our function notation, which I'll just write over here for the sake of room. W equals f of g, meaning w is a function of g, and it's equal to negative 3g plus 6. And this can be done using any variables. That's why I wanted to use w and g, because they're not typically used in this form. Usually it's just x and y. Sometimes you'll introduce other variables like a and b, but this shows you can use any variables you want and function notation will still work. W is a function of g. Okay, now getting back to our normal variables, y and x, We now have another example that says express y as a function of x. So we're going to go through the same process again. We have x squared plus y squared equals 1. To get y alone, because we need y equals f of x, we will subtract x squared from each side, which gives us y squared equals 1 minus x squared. Again, we'll put it in order of exponent. So negative x squared plus 1. And then to get y alone in this case, we need to get rid of that square. So we'll take the square root of each side of the equation, which gives us y equals plus or minus the square root of negative x squared plus 1. Remember, whenever you take the square root of each side, you need a plus or minus. And now notice what happened here. What happens if we were to plug, for instance, 0 in for x? If x equals 0, then that means y equals plus or minus the square root of negative 0 squared plus 1 will just leave us with 1. So y equals plus or minus 1 when x equals 0. Can you think about what's wrong with that statement? We just said we could create 2 points. The point 0, 1 and the point 0, negative 1. Remember, you cannot have a function that repeats x values. We just repeated 0 with different y values. So y is not a function of x. It cannot be written as a function of x. So we would just write no solution, because there is no such function that exists here. The only way for this function to exist is if we restrict the domain values, and that doesn't really start coming into play until we start talking about inverse functions. Okay, so as of now, whenever something like this comes up, we just have to say that there is no solution, no function exists. Okay, and now the last thing that we need to talk about in terms of functions is a very critical method that we use. It's not always easy to prove with this equation format that we just used that something is or is not a function. As you could tell, this problem is pretty difficult, and this was just a very basic type of problem. So imagine when things get really complicated. How can you really prove something isn't a function? Well, this is where the vertical line test comes into play. We say if a vertical line intersects the graph of an equation at more than 1 point, then the equation is not a function. Note that this is any vertical line. If it happens one time in the problem, then that problem is not a function. So looking at this first graph, take a moment, decide if this is or is not a function. Okay, so looking at it, no matter what vertical line we draw through this graph, it will only ever hit the graph at 1 point. So since they only ever intersect at 1 point, that means this is a function. Now how about this second one? Take a moment, pause the video, decide if you can tell whether or not this is or is not a function. Okay, so looking at this graph, if we take the vertical line right here, notice that this intersects the graph at 3 points. If it intersects at more than 1 point, it is automatically not a function. And we only need one case for that to happen. One vertical line and it automatically fails.